Hello everyone, I'm Norman Wildberger, and welcome to this video on how to set up fractions. And we're interested in the question about canonical forms for fractions. And I'm going to show you how that topic connects naturally with the Euclidean algorithm, one of the fundamental procedures from ancient times. So we've set up fractions. They're expressions a over b. A and b are natural numbers, 1, 2, 3, etc. So 0 not included. A over b equals c over d precisely when AD equals BC. So this is the source of a lot of the consternation and sort of practical difficulties with arithmetic with fractions, is that the same fraction can be represented in lots of different ways. So a natural question is, out of all these possible different ways, is there actually a canonical form? Well, the answer is yes. So for example, here are a bunch of fractions, and they're all equal. So you can check equality. And of course, there's many other fractions which are equal to these. And of these various ones, 2/3 is special. It's special because it has the property that the numerator and the denominator have no common factors. So that's really great. That means that we can pick out this canonical or simplest or sort of reduced form and attempt to do arithmetic with these kinds of forms in mind. So this is computationally a big advantage and allows us then to more easily compare the results of my calculation with the results of your calculation and so on. Now all of what we're doing here has a kind of a parallel for those of you who still believe in real number arithmetic. So I'm hoping that you're thinking, well, the things that he's doing now, what does it actually look like correspondingly for these so-called real numbers? And this particular question is very, very pertinent to the difficulties that are manifest in the so-called arithmetic with real numbers. So it's something to think about as we go through this. What is the corresponding theory for real numbers if you really believe such? Now we've seen this lemma before. This is the lemma that allows us to see that when we multiply top and bottom, or numerator and denominator, by a factor r, then the fraction is unchanged. So AR over BR equals A over B. And so that means that we could go from this expression to this simpler one by removing this common factor of r from the numerator and the denominator. Okay, so the numerator is the thing on the left-hand side, and the denominator is the thing on the right-hand side. These are both natural numbers. So we could remove common factors from the numerator a and b of the fraction a over b, and we could keep doing that until there are no more common factors to be removed. Okay, so this leads us to the natural concept of a relatively prime pair of numbers. So natural numbers a and b are relatively prime precisely when they have no common factors. And of course, technically speaking, bigger than 1, because 3 and 4 do have a common factor of 1, but we're obviously not going to include that. So we have this notion of relatively prime, a pair of natural numbers. So now we can make the definition that the fraction a over b is reduced precisely when a and b are relatively prime. Okay, and then it turns out that every fraction can be written in a reduced form, and furthermore that reduced form is unique. So this gives us a canonical form. This is a very attractive aspect now of these multitude of possible expressions for a rational number. There's one that's special, that's simpler than all the others. That's the reduced one. But the question is, how do we do this? How do we actually obtain such a reduced form for a given fraction? We need a method to find the greatest common divisor of the numerator and the denominator of two numbers a and b. And this is the standard notation for that. D is the greatest common divisor of a and b. And what does that mean? Well, it means that D divides, or is a factor of both a and b, and that it's the biggest such common factor. That's the factor that you want to remove or cancel from both numerator and denominator to get the reduced form. So here are some examples of GCDs, or greatest common divisors, which are sort of dual to the earlier examples of least common multiples of two numbers. There's a natural sort of connection between these two these two things. So the GCD of 5 and 15 is 5, because 5 is a divisor or factor of both 5 and 15, and it's the biggest one. The GCD of 12 and 15 is 3. 3 divides both 12 and 15, and there's no bigger number that divides both 12 and 15. In terms of prime factorizations, if we say have 2 to the 7 times 3 cubed times 5 to the 4, and 2 cubed, 3 to the 6, 7 to the 21, then what is the greatest common divisor? Well, it's sort of the opposite of what we did with the least common multiple. With the least common multiple, we looked at sort of the maximum power of any prime that appears. Here we look at the minimum power. So we look at prime 2, it appears with power 7 here and power 3 here, so we take 2 cubed. With 3, there's a 3 cubed here, a 3 to the 6, we take a 3 cubed. 5, there's a 5 to the 4 here, and there's a 5 to the 0 here. So we take the 5 to the 0, which is to say that we don't include any power of 5. And we take 7 to, well, here there's a 7 to the 21, here there's a 7 to the 0, so we don't include any 7. So this is then a factor of both this, you can see that, and it's also a factor of this, and you can't jack this up at all to make a bigger common factor. So this is a technology that works very clearly if you have the prime factorization of A and B in hand. However, this is very challenging if A and B are bigger numbers, because finding the prime factorization of a big number is very challenging, and if once the number gets to be several hundred digits long, it's more or less impossible unless you have a very powerful computer, and once it's several thousand or million digits long, then it's impossible even with a big computer in general. So this is not really a very consistent or conceptually embracing way of getting a GCD. There is another way which is much better and can be extended to bigger numbers more easily, and that goes back to Euclid. It's called the Euclidean algorithm, and it's perhaps the most famous algorithm from antiquity. Okay? It's a step-by-step procedure to find the greatest common divisors of two natural numbers A and B. So we're making contact here with a very significant algorithm from antiquity, from the ancient Greeks. Now, the ancient Greeks thought very geometrically, more than they thought arithmetically. And even their arithmetic was closely tied in with geometrical reasoning. And this is a case in point, so it's nice to illustrate Euclid's algorithm in a geometrical way, because this is probably close to the way he might have thought about it. So in this context, we have two segments, not two numbers, two segments. Okay? Here's the segment A, and here's the segment B. And Euclid's algorithm allows us to find the GCD of these two segments, which is to him another segment which has the property that both A and B are multiples of this third segment. Okay? And moreover, that this third segment is the biggest segment that has that property. Okay, so here's how we're going to do it. We're going to do it geometrically. So I'm going to copy A over here, and I'm going to make B over here. Just copy it so that we have now a rectangle. So we're forming a rectangle with sides A and B. And I'm going to put the larger one down here. So this is A, this is larger than B. And now I'm going to basically peel off a certain number of copies of B from A. And we can do this geometrically by creating little squares. So if we actually had a compass and ruler, we could put our center of the compass here and make a circle here to get this point down here. And then we could put the center here and make a circle like this. And another center here and make a circle like this. And we would get that point there. Okay? So that would allow us to create that square. Then we could extend that to a rectangle. And then we could sort of duplicate that. Here's another copy of this square. So that's guaranteeing that this side is also B. This side is also B. So here we have 2B. Now we can't do this a third time because then we'd go beyond A. So there's something left over. Okay, and what's left over is this new rectangle, one of whose sides is B, and the other side, let's call it C, is what you get when you take A and you remove 2 copies of B. So now what Euclid does is he says, okay, the problem of finding a sort of commensurable unit, or a unit which is a factor of both A and B, reduces to the problem of finding a unit which is commensurable with B and C. So let's take this rectangle and sort of put it on its side over here so that the long side, which is B, is horizontal, just as we started with. Okay, so this is supposed to be a copy of this one here. And here's C, this new segment is now there. Okay, now we're going to do the same thing that we did before. We're going to peel off a certain number of C's from B. B is bigger than C. Okay, so we're going to peel off, there's one C that we can peel off. And actually that's as far as we can go, because if we go further, we go beyond B. So having done that, there is then a new sort of leftover or remainder rectangle that is occurring, and we could assign its new dimension to be, say, D. So the dimensions of this thing now are C and D. Okay, so now let's take this thing here and put it down there. So again, C, the long dimension is down horizontal, and the vertical dimension is D. So the problem of finding a sort of a commensurable unit with A and B has now been reduced to finding a commensurable unit for this smaller rectangle with sides C and D. So we do the same thing again. We peel off 1 square and 1 square, so there's 2 copies of D represented there, and then there's a little bit of a remainder. Let's call that E. So there's the remainder rectangle. Okay, and then we flip that onto its side, so the long dimension D is down there and the small dimension E is up there, and we see how many of these E's can fit in here, and we see 1, 2, 3, 4, 5, exactly 5 of them fit. Exactly 5 with no remainder. So now the process happily stops. And now we can see that this unit E, which was sort of the last new thing that we obtained, is the required unit that has the property that a multiple of it is A and another multiple of it is B. Now, this might be easier for the modern viewer to appreciate if we write it down algebraically. Okay, so let's look at the corresponding equations to these diagrams. The first diagram, we were really taking A and we were essentially dividing it by B. We're saying that A is equal to 2 times B plus some remainder of C. Okay, and then in the next diagram, we were taking B and essentially dividing it by C, saying, okay, B is equal to 1 times C plus a remainder of D. And then in the next step, C is divided by D, goes 2 times, plus a remainder of E. And in our final little diagram, we had D here, we divided it by E, we got 5E plus a remainder of 0. No more remainder. So no more remainder, and the algorithm terminates. Okay, so now let's look at this, look at these 4 equations and see what we can deduce about the relationship between the original A and B and this sort of new unit E. So I might do it up here. So let's go back up this thing here. If we start with the bottom, we see that D is equal to 5E. Okay, so that's, we know. What about C? Okay, so D is equal to 5E. So imagine replacing D with 5E there. You're going to get 10E here, plus another E there. So that makes 11E. So C is actually 11 times E. What about B? Well, B is equal to 1 times C plus D. So C is 11E, that's 11E, and D is 5E, so C plus D is 16E. B then is 16E. Okay, good. And finally, what about A? A is equal to 2 times B plus C. So 2 times B plus C. So 2 times B is 32E plus C is 11. So 32 plus 11 is 43. So 43E. A is equal to 43E. And since we were starting with A and B, that's what we were really interested in. So the two results that we're really interested in are these last two. That A is actually 43 times E, and B is actually 16 times E. So we found this unit of commensurability. If we sort of think of this as being now a unit length, then A and B are both integral multiples of E. 43 times E and 16 times E. And I want you to appreciate that this geometrical construction actually doesn't really require any knowledge of arithmetic, really. So we could explain this to a primary school student in such a way that it doesn't rely on a prior theory of arithmetic. I mean, we've analyzed it, with some arithmetic, but we could also just sort of analyze it by ordinary counting, but not any algebra or real arithmetic. It's a geometrical manifestation of the Euclidean algorithm, and this is pretty close, I think, to the ancient Greeks' orientation of quantities as being primarily geometrical things, typically represented by line segments. So now let me show you the arithmetical form of Euclid's algorithm, which will be more familiar if you've learned about these in, say, an undergraduate course. It is usually an undergraduate topic. I'm not sure if it's much studied in high school. I mean, probably some places it is, but I'm not convinced that it's an essential part of the high school curriculum generally. Okay, so the arithmetical form of Euclid's algorithm, let's start with two numbers. So A is 183 and B is 22. Okay, so we're interested in the GCD. That's like the arithmetical equivalent of that E segment that we obtained in the previous example. So what do? We divide the bigger one by the smaller one. So 183, if we divide it by 22, it goes 8 times. 8 times 22 is 176. 176, so there'll be a remainder of 7. Okay, so like if this is A and this is B, then this is like C that we obtained previously. Okay, so now the next step, we are looking at B and C. So 22, we're going to divide it now by 7. It goes 3 times with a remainder of 1. Okay, like this, and then sort of like D. And then we take 7 and 1, we divide 7 by 1, it goes 7 times with a remainder of 0. So the last non-zero remainder that we got was this 1. Okay, that's the last non-zero remainder that we got. And then all of the numbers are multiples of 1, and that's the GCD of 183 and 22. What does that mean? It means that 183 and 22 actually have no common factors, aside from 1, which means they're relatively prime. And so the fraction 183 over 22 is reduced. We know that there's no common factors that we could possibly divide top and bottom by to get a simpler, more reduced fraction. So that's the Euclidean algorithm, showing that in this case these two numbers are relatively prime because their GCD is 1. Let's look at another example where the GCD doesn't turn out to be 1. So A is 1,846 and B is 247. So somewhat bigger now. So let's divide A by B. 1,846 turns out to be 7 times 247 plus a remainder of 117. So that's like the C in the first example. So now we shift from thinking about A and B to thinking about B and C. So we divide b with c. C is smaller than b because it's a remainder after you've divided by 247. So this is definitely smaller than that. So we divide by it, and we get 247 is 2 times 117 plus a remainder of 13. So this is then the analog of d. So now we shift our attention to c and d, if you like. We're going to divide 117 by 13. It goes 9 times. 9 times 13 is 117 plus no more remainder. No more remainder. So the last non-zero remainder that we got was this 13. And that's telling us that 13 is the greatest common divisor of the two original numbers a and b. And we could now go back and figure out, what multiples of 13 are required to get 247 and 1,846. Right? So how you would do that. So from this thing here, the 117, you'd replace it with 9 times 13. And so you get altogether 18 times 13 here. And there's another 13. So that's altogether 19 times 13. So this thing here is 19 times 13. And then you'd plug that into here. So you put in a 19 here. Okay. And over here you put a 9. So then there'd be 19 times 7, and then plus another 9, and that turns out to be 142. So going backwards, going back up, you can see that the a is 142 times 13. That's the multiple of the GCD required to get the numerator. And 247 is 19 times 13. So we're doing a little bit more here. It's not just that you have to stop when you get the GCD. You have to kind of go back and either do another division or sort of go back up the tree to see just how many multiples of the GCD are required to get the original numerator and denominator. And that's important because after then we cancel this GCD, the remaining reduced fraction will just be 142 over 19. The 13 disappears, and then we get this simplification that the original fraction is now in reduced form 142 over 19. So that's the way you reduce a bigger fraction. And you can see that this is non-trivial. Okay? So if you're going to teach students an effective arithmetic with fractions, you really want them to appreciate the importance of a canonical or reduced form. And if you want to give them a real technology that actually works more generally, not just in the low cases when you can factor numbers, then you have to teach them the Euclidean algorithm. You have to go back to Euclid. So you can see why primary school teachers have such a challenge ahead of them to present a coherent and workable theory of fractions. Now, I'm not saying that primary school students have to be exposed to all of this, but primary school teachers and high school teachers should be aware of all these issues that I've brought up. Okay? So it's not just having a theoretical foundation for fractions. We also have to understand moving to mixed fractions. We have to appreciate the alternate technology of using least common multiples for addition. And crucially, we have to have some understanding of the Euclidean algorithm to be able to systematically get reduced forms for fractions. Because otherwise, computations just blow out. You get just these huge numerators and denominators, and nobody has even the faintest idea, more than rough, about what quantities these really represent. And whether your big fraction is the same as my big fraction is the same as Jane's big fraction. So effective arithmetic with fractions is actually quite hard. And it's no surprise that students find it challenging and that primary school educators often, struggle to do this in an effective way. So I think these issues really need to be sort of front and center. This is a very, very important topic for primary school education. Now, because this is so important, in my next video, I want to place sort of arithmetic with fraction in a larger context of how it fits into our other numerical systems. So it turns out that we have actually quite a few different numerical systems, and how they interact and how they relate to each other is very important. And that's part of the story of understanding fractions in an effective fashion. Hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.